Hello, in this video we're going to do a problem to practice integration, and the question is to evaluate this triple integral of x over x squared plus y squared, where D is the region in the first octant bounded by the sphere x squared plus y squared plus z squared equals 9 and the planes x equals 0, y equals 0, and z equals 0. So first let's get an idea of what this region looks like. By the way, I would encourage you to try to do the problem on your own first, and then we'll go over the answer. So D is in the first octant, and you have the sphere x squared plus y squared plus z squared equals 9. That's a sphere of radius what? 3, right? Because x squared plus y squared plus z squared equals r squared is a sphere centered at the origin of radius r. So you have radius 3. But you only want the part that's bounded by the sphere that's in the first octant. And it's bounded by the planes x equals 0, y equals 0, z equals 0. Well, that's in the first octant, right? So you're going to have something like this. And it's a solid in the first octant. It's going to be like this wedge. It's going to look like well, it's going to go down, and then it's, I don't know, it's going to be hard to draw, but here's the back, and then it's going to go like this. It's going to be like this. It's basically if you take a ball centered at the origin with radius 3 and then only look at the part that's in the first quadrant, you're going to get this shape. Right, so this is in the x direction, that's in the z direction, that's in the y direction. That's the solid D. And you want to evaluate this triple integral. Well, what should we do to evaluate this triple integral? We should use spherical coordinates, right? Because spherical coordinates are what's useful when you're integrating over well, this is a solid ball that's consisting of a bunch of spheres. And this is centered at the origin. So how does it work? It's x equals, what's the conversion? X equals rho sine phi cosine theta and you have an x squared plus y squared. Let's see, y equals rho sine phi sine theta. Right? And then z, well, we don't have z here. And let's just remind ourselves that rho is the distance from 0. It's the distance from the origin out to the sphere. That's your rho. It's the distance from the origin. Theta is the angle that's made with the positive x-axis. And then phi is the angle that's made with the positive z-axis when you go down. Okay, so now we need to substitute this into our function. And we need the dv. dv is equal to rho squared sine phi d rho d phi d theta. and we need to do the integral. So this x over x squared plus y squared, okay, let's just figure out what that is first. It's rho sine phi cosine theta over x squared plus y squared is going to be, you see what you're going to get? You're going to get rho squared sine squared phi cosine squared theta plus rho squared sine squared phi sine squared theta. But then you can factor out a rho squared sine squared phi out, and then you're going to get cosine squared theta plus sine squared theta. Cosine squared theta plus sine squared theta is 1, right? That's equal to 1. So this is going to be rho sine phi cosine theta over rho squared sine squared phi. And I can cancel out the rho and one of the sine phi's, and I'm going to be left with cosine theta over rho sine phi. But then I have to multiply that by the I have the dv term. So I'm going to get cosine theta over rho sine phi times rho squared sine phi d rho d phi d theta. And I'm integrating. So what's my d rho? What are my bounds of integration for rho? I'm going from 0 to 3, right? So rho goes from 0 to 3. What about phi? Phi is going from 0 to pi over 2, right? Because it's starting here, and then it's going out to here. You get a 90-degree angle. So it's 0 to pi over 2, and then theta goes from what to what? Theta is going from 0 to pi over 2 also, because you're starting with the positive x-axis, and then when you go counterclockwise on the xy plane, you stop when you get to 90 degrees, which is pi over 2. So we have to evaluate this integral. That's the integral we get when we convert to spherical coordinates. And now I see that I can do some simplification. I have a rho sine phi here. I can cancel the rho and the sine phi. So I really end up getting the integral of rho cosine theta. Now, when you have something like this, you could do the inner integrals and then do each of them out. But when you have something where you have, see, in this case, you have something where you have a function of rho times the function of phi and the function, excuse me, times the function of theta. When you have that, you can just do the integrals separately and multiply them. Because when you're integrating, so for instance, if you integrate with respect to rho, that's the inside one, your theta is going to be constant, so you end up pulling it out. And that explains basically why you can rewrite this triple integral as a product of 3 different integrals. So you have the integral with respect to rho, and that's going to be, so I have a rho here, right? I have this rho. So I'm going to get rho d rho from 0 to 3. I have to do this integral, and then I have to multiply by the integral with respect to phi, and my phi term is just 1 because I don't have a phi term. So phi is just going from 0 to pi over 2, right? I'm just multiplying by 1, and then my theta term is cosine theta. So I have the integral from 0 to pi over 2 equals cosine theta d theta. And now we can evaluate each of these separately. The integral of rho is going to be 1/2 rho squared from 0 to 3. And then for phi, I just have phi from 0 to pi over 2. And then I have sine of theta from 0 to pi over 2. And this 1/2 rho squared is going to give me 9 over 2. This phi is just going to give me pi over 2. And then the sine of theta is going to give me sine of pi over 2 minus sine of 0. Well, sine of pi over 2 is 1. So I have this. Oh, did I do something wrong? Let's see. Sine of pi over 2. Oh, yeah, no, this is correct. It's, 9 pi over 4. Sorry, I'm just looking at something else and there's a typo. Yeah, it's supposed to be 9 pi over 4. This is correct. So that's the integral. Okay, and of course it makes sense that we get a positive answer because we're integrating a function. So we're integrating this function and then we're integrating over a part where x and y are positive. So this function is always positive, and so the integral should be positive. Okay. So that's an example with spherical coordinates. It's a relatively easy example because you're actually just integrating over a solid ball, a part of it that's centered at the origin. That's one of the easier spherical coordinate examples. Okay, thanks.